Good afternoon. Today I am going to discuss the NMR spectroscopy, that is nuclear magnetic resonance spectroscopy, and spectroscopic method is used for the determination of structure of organic molecules. We generally used IR, NMR, UV spectroscopy and also mass spectroscopy for the determination of the structure of organic molecules. The IR, UV and NMR spectroscopy are absorption spectroscopy, but the mechanism of absorption are different in case of IR, NMR and UV spectroscopy. Now I am going to discuss the nuclear magnetic resonance spectroscopy. The nuclear of certain isotope possesses mechanical spin or angular momentum. It deals with the nucleus which is magnetic in nature, that is those nuclei which have spin number is not equal to 0, that is I is not equal to 0, and spin number depends on the mass number and atomic number of the atoms. Say the mass number when is odd and atomic number even or odd, that is for example proton 11H and beryllium 49 and carbon C13, their spin number are half, 3/2 and 5/2. Their spin number is not equal to 0, so they are NMR active. Now if the mass number is even and atomic number is even, that is example is C612O816, their spin number is 0. So they are non-magnetic and the net spin about the axis is 0, and so they are NMR inactive. So they cannot be used in the nuclear magnetic resonance spectroscopy. And when the mass number is even and atomic number is odd, their spin number is 1, 2, 3, etc., and they are also NMR active. Now, when this type of spinning nucleus whose spin number is not equal to 0 is placed in an external magnetic field B0, it can take up a number of possible orientations, and the number of possible orientation are characterized by different energy levels. Let us consider proton, that is H11. The number of possible orientation equal to 2s, that is 2i plus 1, 2 into half plus 1, that is equal to 2. So in case of proton, number of possible orientation is 2. One orientation is lower energy orientation and another orientation is higher energy orientation B. One is parallel to the external magnetic field, another is anti-parallel to the external magnetic field, and the difference between these two levels, this is A and this is B, and the difference is del E. Del E is very, very small, and it is also important that excess of nuclear, that is 0.001% nucleus are always present in the lower energy level, because when absorption takes place it gives a signal, and we want continuous signal, so always an excess nuclear remains in the lower energy level. Now mu is the magnetic moment of the nucleus, so the energy level can be represented by plus minus mu B0, and we know that the del E is equal to h nu is equal to 2 mu B0, h is equal to 2 mu B0, and nu, that is the frequency, is equal to 2 mu by h B0, and 2 mu into 2 pi by h and into B0 by 2 pi. So we replace this one by gamma. Gamma is the gyromagnetic ratio that is constant for a particular nucleus, and B0 by 2 pi. So, frequency versus strength of the external magnetic field. So, frequency increases, strength of the external magnetic field increases, strength of the external magnetic field increases, frequency increases. When B0 is 14,000 Gauss, then the frequency is 60 megacycles per second. Now, when a spinning nucleus is placed in an external magnetic field, so what's happening? Spinning nucleus draws out a circle making angle theta with its axis and moves in this orbit. This orbit is called as precessional orbit, and the motion in which the spinning nucleus moves is called precessional motion. Now, another external magnetic field coming from the radio frequency oscillator, that is rotating magnetic field, whose magnetic vector is perpendicular to the magnetic vector of the external magnetic field, is applied on the spinning nucleus. Then, and when the frequency of the rotating magnetic field is equal to the frequency of the preceding nucleus, then and only then the nucleus is said to be in resonance and it absorbs energy and it flips from lower spin state to another nuclear spin state. That is, lower energy state nucleus, spinning nucleus absorbs energy h nu and flips to the higher energy state. Absorbing from RF radiation causes the nucleus to flips. Okay. Now, according to Boltzmann distribution, 0.001% nucleus remains always in excess in lower energy state. Now, how it is maintained? There are some processes. One of the processes is the radiation-less process, that is relaxation process. Relaxation process maybe two types. One is spin-spin relaxation and another is spin-lattice relaxation. Now, what is spin-spin relaxation? Spin-spin relaxation, when two spinning nucleus come closer to each other, they exchanges their energies and relaxes. So, there is no question for maintaining this excess nuclear in the lower energy state. But in the second type, this is spin lattice relaxation. Spinning nucleus gives its energy to the lattice and comes down to the lower energy level and maintained the excess nuclei in the lower energy level. This is a line diagram of NMR spectrometer. Sample is taken in the sample tube and we obtain spectra here. Now, the sample is first dissolved into a solvent. Which type of solvent? Solvent used for dissolving sample should have following properties: should not contain proton, inexpensive, and low boiling and non-polar in nature. Generally, we use CdCl3, and sometimes we use also this type of solvent, that is CCl4, CH2, etc. But we generally use CdCl3. So sample is resolved into CdCl3, and then we add a standard reference. Standard reference, that is internal standard, that is tetramethylserine, TMS. Why it is used? TMS is most commonly used as internal standard because it is chemically inert and miscible with a large range of solvent, and it contains 12 protons which are magnetically equivalent, and its protons are highly shielded and gives a strong peak even small quantity, and it is less electronegative than carbon. It is highly volatile and can be easily removed to get back the sample. It does not take part in intermolecular associations with samples, and its resonance position is far away from the absorption due to the protons in most organic molecules. Thus, signals of TMS is taken as 0. So we take sample and dissolve the sample, few drops of CdCl3 was added, and then very small quantity of TMS is used, is added to it, and we obtain this type of spectra. And NMR spectra is a plot of intensity of a peak against its chemical shift. Intensity here, and this is the chemical shift measured in parts per million, that is ppm, and also it is delta, it is called delta scale. And this is the signal for, this is the absorption of 12 proton of TMS. This is the standard reference, it is TMS, and we take this as value is delta 0, then 1, 2, 3, 4, 5, 6, etc. This is called chemical shift. What is chemical shift? Chemical shift is the difference of the absorption peaks of the protons of the organic compounds with respect to the TMS, that is the difference, is called chemical shift. So we say that the chemical shift value of this one is 1, this proton is 3, etc. Now you see that this is upfield direction. When towards TMS, we call upfield, and away from the TMS, we call downfield. Now the protons in organic compounds are surrounded by bonded electrons. So bonded electrons when it placed in the external magnetic field, it produces an induced magnetic field. It produces a nucleus is surrounded by the electrons, bonded electrons also, and it produces a induced magnetic field which is opposite to the direction of the applied magnetic field, that is B0, opposite. So the induced field decreases the strength of the magnetic field felt by the nucleus, and we said that the nucleus is shielded. Now as the nucleus density around the nucleus increases, what happens? The nucleus feels a smaller resultant field because they produce a larger induced magnetic field, so it feels a smaller resultant magnetic field, and the nucleus feels a smaller resultant magnetic field, so a lower frequency is needed to achieve the resonance, and the absorption shifts towards upfield. As the electron density around the nucleus decreases, what's happened? A smaller induced magnetic field. It produces a smaller induced magnetic field, and the nucleus feels a larger resultant fields. So higher frequency is needed to achieve resonance and the absorption shifts downfield. So two terms is very important, upfield and downfield. Now the chemical shift depends upon the following parameters. One is electronegativity of nearby atoms, hybridization of adjacent atom, and diamagnetic effects from adjacent pi bonds. Now first one, electronegativity. In this table, you see methyl fluoride, methyl chloride, methyl. I am taking just methyl fluoride, methyl chloride, and methyl bromide. Methyl fluoride, CH3F, CH3Cl, CH3Br. Now the chemical shift value of this proton and this proton is delta 4.26. For this proton it is 3.05, delta 3.05, and then for CH3Br it is delta 2.68. Now we know that the fluorine is more electronegative than chlorine, chlorine is more electronegative than bromine. So electronegativity increases in this way. Fluorine is most electronegative among fluorine, chlorine and bromine. Fluorine draws electrons towards itself. So what happens? Electron density decreases here. Right? So electron density decreases on the proton of CH3 group. So electron density around the nucleus decreases and the nucleus feels larger, result in magnetic fields. So a higher frequency is needed to achieve the resonance and absorption shifts to downfield. You see that this is 4.26. Chlorine is less electronegative than fluorine. So here the electron density around the nucleus increases comparatively to CF3. So electron density around the nucleus increases and the nucleus feels smaller resultant magnetic field. So a lower frequency is needed to achieve resonance and the absorption shifts upfield. That is value is 3.04. Similarly, for bromine it is delta. It is also another upfield shift. So it is absorption occurs at delta 2.68. Now the hybridization of adjacent atom. I am taking 3 compounds from this table. You see that the R3CH absorbs, that is aliphatic proton, absorption occurs at delta 0.82, more or less 1.7, okay, this proton. And I am taking this compound, that is ethylenic proton, R2C double bond CH2. The value is delta 4.62, 5.7. And also taking RCHO, aldehydic proton, value is quite downfield, 9.5, 10.1. Now, in case of ethylene, say C double bond C, the molecules are always moving into the system, and the molecules which are perpendicular to the external magnetic field. So we are taking this molecule which is perpendicular to the external magnetic field, ethene, C double bond C. So these pi electrons produced induced magnetic field, and it is diamagnetic, is opposite to that of the external magnetic field. It is parallel, so it is paramagnetic. Diamagnetism, paramagnetic. When it is perpendicular to this external magnetic field in this orientation, induced magnetic field obtained from the circulation of pi electrons opposes the magnetic field, and so this is the diamagnetic positions, and the carbon atoms in the diamagnetic zone, but the protons are in the paramagnetic zone. When it is paramagnetic, it is more deshielded, and deshielding takes place, and comes at downfield, that is delta 4.6 to 5.7. So this is deshielding zone, this compound. Anisotropic shielding and deshielding around the alkene groups. Anisotropic means the position of the proton in space. So this proton falls into the shielding zone, and we obtain the value delta 4.6 to 5.7. And similarly, in case of aldehyde, value is 9.5 to 10.1. This is also in the deshielding. From this proton falls into the deshielding zone and absorb at delta 9.5 to 10.1. And also the benzene ring, in benzene ring, pi electron circulates in this way, circulation of electrons, and it produces induced magnetic field. So this is shielding zone, and the paramagnetic in this region, and the hydrogens are in the paramagnetic zone and deshielded, and this value comes nearly 5.66 to 8 delta. Now, in case of acetyl proton, it comes delta 2 to delta 3. Now, what's happened here? there are two orientations are possible in case of acetylene. You see, it is longitudinal and it protons here, that is protons in the diamagnetic zone, and you see here induced paramagnetic and resultant diamagnetic falls in term resultant diamagnetic. So it comes at acetylene proton comes at delta 2.0, nearly 2.0 delta. Now what type of information we get from 1H NMR spectroscopy? That is the number of signals indicates how many different types of hydrogens are present in the molecule, and the position of signal, that is the chemical shift, indicates what types of hydrogens are present, and the relative areas under signals integration, how many hydrogens of each type, and splitting pattern, that is how many neighboring hydrogens are present in the molecule. Number 1, number of signals. In cyclohexane, there are 12 hydrogen, but they are magnetically equivalent. In the benzene ring, it contains 6 hydrogen, but they are magnetically equivalent, so it gives one signal, whereas they are magnetically equivalent. This 12 proton gives one signal, but there is two types. One is 4 hydrogen and another is 6 hydrogen here, 2. So 2 types of signal can be obtained here. It depends on the magnetic nature of the proton present in the molecule. Here, the first one, these 6 protons are magnetically equivalent, but in this case, this is a type of proton, another type of proton, and another type of proton. So we get 3 signals for this purpose. Similarly, 2 and then 2. So in this case, we get 9 equivalent hydrogen, we get 9 proton singlet. In this case, we get 3 proton triplet. That is the splitting pattern, which I shall discuss later on. 2 proton complex and 2 proton triplet for C. Here, CH3, CH is triplet, for type 2, it is 2H quartet, and in this compound, this carbon atom contains 3 hydrogen atom, and this carbon atom, these 2 are A type, so total is 6 hydrogen, and it gives doublet, whereas this carbon atom gives septet. And now how the splitting pattern? Ethyl alcohol. This comes at about 1.7 delta. This comes about delta 3.6. Now you see that they say this one C1 and this is C2 carbon atom. C1 carbon atom contains 3 proton, C2 carbon atom contains 2 proton. In case of 1, CH3, protons couples with the magnetic field coupled with this is C1, C2 carbon atom containing 2 protons. It has been found that the C1 protons experiences the magnetic field of C2 protons and couples. How? It contains 3 proton and C2 carbon contain 2 protons, and it couples and gives N/1 rule, and N is equal to the number of proton on adjacent carbon atom. In case of CH3, number of protons on adjacent carbon atom is 2, that is 2 plus 3, 2 plus 1, that is equal to 3. That is, it gives a triplet. So it gives 3 proton triplet. What is triplet? Triplet is in this type of ratio of this peak is 1:2:1. Similarly, the proton of C2, that is CH2, experiences the magnetic field of C1 carbon atoms and gives 2 proton quartet. 2 proton quartet means ratio is 1:3:3:1. And this proton depends on the solvent exchange, and also this comes different value, different type of absorption in the IR spectrum. I am just showing the spectrum of ethanol. So it is A type, C type, and B type. A type gives 3 proton triplet, and C gives 2 proton quartet, 2 proton quartet. You see that the triplet, and that is 1.7, 1.7, and here 3.6, 2 proton quartet is coming over here, and H comes here, that is 2.5 range. So we can determine the structures of compound by analysis of nuclear magnetic resonance spectroscopy, by using nuclear magnetic resonance spectroscopy. This is the spectrum for ethyl bromide, tertiary butyl bromide. All are magnetically equivalent protons and gives 9 proton singlet. And the amount of proton can be obtained from the integration amount of the proton can be obtained this type of graphs. We obtain the number of protons by calculating the square area of from this graph. Okay, thank you very much.